it is not permissible to use number 8 THHN conductor on a 225 amp circuit breaker to feed a 45 kVA transformer. National Electrical Code NEC Article 240.4e prohibits the use of a conductor smaller than the ampacity of the overcurrent device protecting it. In this scenario, the breaker is rated at 225 amps, necessitating the use of a number 2 THHN conductor following Table 310.15b16. NEC Article 240.101 provides allowances for conductors to be oversized by a factor of up to 3 times their ampacity for transformers, subject to specific conditions. Firstly, the transformer's rating must not exceed 112.5 kVA. Secondly, the conductor must be safeguarded by an overcurrent device with a trip setting that does not exceed 3 times the conductor's ampacity. Given that the transformer is rated at 45 kVA, it does not exceed 112.5 kVA, and the provisions of 240.101 do not technically apply. The inrush current of the air compressor is a critical factor to consider, particularly during startup, as it can be substantial. This inrush current is capable of tripping the 225 amp breaker, even if the conductor were oversized by 125%. The use of a time delay fuse on the secondary side does not provide complete protection for the transformer's primary side. The fuse will only trip if the current surpasses the fuse rating for a sustained duration. The inrush current might still exceed the transformer's primary rating, which can lead to damage. To safely power the air compressor, using a number 4 THHN conductor on a 250 amp circuit breaker is recommended. This configuration ensures adequate capacity for the transformer's primary current and provides protection against inrush current. The selection of wiring and overcurrent protection for transformers and motors is governed by the National Electrical Code, which provides guidelines to ensure safety and prevent equipment damage. The NEC outlines requirements for conductor ampacity, overcurrent device sizing, and protection against short circuits and ground faults. When dealing with transformers, the primary concern is to protect the transformer itself from overcurrent conditions. The NEC permits the overcurrent device on the primary side of the transformer to be sized based on the transformer's primary current rating rather than the conductor's ampacity. This is because the transformer's primary winding is designed to withstand a certain amount of overcurrent for a short period. However, it is crucial to select a conductor with sufficient ampacity to carry the transformer's primary current continuously. NEC Table 310.15b16 provides ampacity ratings for various conductor sizes based on insulation type and installation conditions. THHN conductors are commonly used in electrical installations due to the high temperature rating and resistance to moisture and chemicals. When sizing conductors for transformers, it is essential to consider the transformer's kVA rating, primary voltage, and secondary voltage. The primary current can be calculated using the formula I equals kVA times 1000 divided by volts times the square root of 3 for three-phase systems. The conductor's ampacity must be equal to or greater than the calculated primary current. In the case of motor circuits, the NEC requires conductors to be sized at 125% of the motor's full load current rating. This is to account for the motor's starting current, which can be significantly higher than its running current. The overcurrent device for a motor circuit must also be sized appropriately to protect the motor from overloads and short circuits. Time delay fuses or inverse time circuit breakers are commonly used for motor protection, as they allow for the motor's starting current to pass without tripping the device. The specific requirements for motor circuit protection can be found in NEC Article 430. When selecting overcurrent devices for transformers and motors, it is crucial to consider the equipment's inrush current characteristics. Inrush current is the high initial current that flows when the equipment is first energized. Transformers and motors can have high inrush currents, which can trip overcurrent devices that are sized too closely to the equipment's normal operating current. To prevent nuisance tripping, it is often necessary to use overcurrent devices with higher interrupting ratings or time delay characteristics. The NEC provides guidelines for sizing overcurrent devices to accommodate inrush current. In addition to conductor ampacity and overcurrent protection, grounding is another critical aspect of electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trip over current devices and prevent electrical shock hazards. The NEC requires all electrical equipment to be properly grounded, including transformers, motors, and enclosures. Grounding conductors must be sized according to NEC Table 250.122, which is based on the size of the overcurrent device protecting the circuit. Proper grounding techniques are essential for ensuring electrical safety and preventing equipment damage. In summary, selecting the appropriate wiring and overcurrent protection for transformers and motors requires careful consideration of the NEC requirements, equipment ratings, and inrush current characteristics. It is crucial to consult the NEC and other relevant standards to ensure that the electrical installation is safe and compliant. Improperly sized conductors or overcurrent devices can lead to overheating, equipment damage, and electrical hazards. It is always recommended to consult with a qualified electrician or electrical engineer to ensure that the electrical installation meets all applicable codes and standards. The NEC provides comprehensive guidelines for electrical installations, and it is essential to stay up to date with the latest revisions. The NEC is updated every 3 years to reflect changes in technology and industry best practices. By following the NEC requirements and consulting with qualified professionals, it is possible to create a safe and reliable electrical system for transformers and motors. The specific NEC articles and tables mentioned in this discussion provide detailed information on conductor ampacity, overcurrent device sizing, and grounding requirements. It is important to refer to these resources when designing and installing electrical systems. In addition to the NEC, other relevant standards and guidelines may apply depending on the specific application. These standards may include those published by organizations such as the Institute of Electrical and Electronics Engineers, i.e., the National Fire Protection Association, NFPA, and Underwriters Laboratories, HUL. It is essential to be familiar with all applicable standards and guidelines to ensure that the electrical installation meets all safety and performance requirements. The selection of electrical equipment should also be based on its suitability for the intended environment. Factors such as temperature, humidity, and exposure to corrosive substances can affect the performance and lifespan of electrical equipment. It is important to choose equipment that is rated for the specific environmental conditions in which it will be installed. Proper installation practices are also essential for ensuring the safety and reliability of electrical systems. Conductors must be properly terminated and supported, and enclosures must be properly sealed to prevent the ingress of moisture and contaminants. All electrical connections must be tight and secure to prevent overheating and arcing. Regular maintenance and inspection are also important for maintaining the integrity of electrical systems. Electrical equipment should be inspected periodically for signs of damage, wear, or corrosion. Any damaged or worn equipment should be repaired or replaced promptly. Electrical connections should be tightened periodically to prevent loosening and overheating. By following these guidelines, it is possible to create a safe and reliable electrical system for transformers and motors. The information provided in this discussion is intended for general guidance only and should not be considered a substitute for professional engineering advice. It is always recommended to consult with a qualified electrical engineer or electrician to ensure that the electrical installation meets all applicable codes and standards. The safe and reliable operation of electrical systems depends on proper design, installation, and maintenance practices. By following the NEC requirements, consulting with qualified professionals, and adhering to industry best practices, it is possible to minimize the risk of electrical hazards and ensure the long-term performance of electrical equipment. The primary voltage is the voltage on the input side of the transformer, while the secondary voltage is the voltage on the output side. The turns ratio of the transformer is the ratio of the number of turns in the primary winding to the number of turns in the secondary winding. The turns ratio determines the voltage transformation ratio of the transformer. For example, if a transformer has a turns ratio of 2:1, the secondary voltage will be half of the primary voltage. Transformers are used to step up or step down voltage levels to match the requirements of different electrical equipment. Step-up transformers increase the voltage, while step-down transformers decrease the voltage. Transformers are essential components in power distribution systems, as they allow electricity to be transmitted over long distances at high voltages and then step down to lower voltages for use in homes and businesses. The kVA rating of a transformer is a measure of its apparent power capacity. Apparent power is the product of voltage and current, and it is expressed in volt-amps, VA, or kilovolt-amps, kVA. The kVA rating of a transformer indicates the maximum amount of power that the transformer can deliver without exceeding its temperature limits. Transformers are designed to operate within a specific temperature range, and exceeding this range can damage the transformer. The inrush current of a transformer is the high initial current that flows when the transformer is first energized. Inrush current can be several times higher than the transformer's normal operating current, and it can cause overcurrent devices to trip. The magnitude and duration of the inrush current depend on several factors, including the transformer size, impedance, and the point in the voltage waveform at which the transformer is energized. To prevent nuisance tripping due to inrush current, it is often necessary to use overcurrent devices with higher interrupting ratings or time delay characteristics. The impedance of a transformer is a measure of its opposition to the flow of alternating current. Impedance is expressed in ohms and is a combination of resistance and reactance. The impedance of a transformer affects its voltage regulation and short-circuit current. Voltage regulation is the change in secondary voltage from no load to full load conditions. A transformer with low impedance will have better voltage regulation than a transformer with high impedance. Short-circuit current is the current that flows when the secondary terminals of the transformer are short-circuited. A transformer with high impedance will have lower short-circuit current than a transformer with low impedance. The type of insulation used in a transformer affects its operating temperature and lifespan. Transformers are typically insulated with oil, paper, or epoxy. Oil-filled transformers are cooled by circulating oil through the transformer core and windings. Paper-insulated transformers are cooled by air or forced air. Epoxy-insulated transformers are cooled by conduction. The choice of insulation depends on the transformer's size, voltage rating, and operating environment. The type of core material used in a transformer affects its efficiency and size. Transformers are typically made with laminated steel cores or amorphous metal cores. Laminated steel cores are made from thin sheets of steel that are stacked together to reduce eddy current losses. Amorphous metal cores are made from a non-crystalline alloy that has lower losses than laminated steel. The choice of core material depends on the transformer's efficiency requirements and cost. The connections of a transformer determine its voltage and current ratings. Transformers can be connected in various configurations, including delta, Y, and open delta. Delta connections provide a three-phase output with a fixed voltage. Y connections provide a three-phase output with a neutral point. Open delta connections provide a three-phase output with reduced capacity. The choice of connection depends on the application requirements. The protection of a transformer is essential to prevent damage from overloads, short circuits, and other faults. Transformers are typically protected with fuses, circuit breakers, and protective relays. Fuses are used to protect against overloads and short circuits. Circuit breakers are used to protect against overloads, short circuits, and ground faults. Protective relays are used to detect abnormal conditions and trip the circuit breaker. The grounding of a transformer is essential for safety and to prevent electrical shock hazards. Transformers are typically grounded to earth through a grounding electrode. The grounding electrode provides a low impedance path for fault current to flow back to the source, which helps to trip the overcurrent device and prevent electrical shock hazards. The maintenance of a transformer is essential to ensure its long-term performance and reliability. Transformers should be inspected periodically for signs of damage, wear, or corrosion. The oil level in oil-filled transformers should be checked regularly, and the oil should be tested for contaminants. The bushings and connections should be cleaned and tightened periodically. By following these maintenance practices, it is possible to extend the lifespan of a transformer and prevent costly repairs. The NEC provides comprehensive guidelines for the installation, operation, and maintenance of transformers. It is essential to consult the NEC and other relevant standards to ensure the transformers are installed and operated safely and reliably. Improperly installed or maintained transformers can pose a significant safety hazard and can lead to costly equipment damage. It is always recommended to consult with a qualified electrical engineer or electrician to ensure the transformers are installed and maintained in accordance with all applicable codes and standards.